All right. Question 4 is asking whether the statements given are true or false. And if they're false, correct them or explain why. And if they're true, give an explanation as well. So part A makes the claim that x to the 3 times x to the 4 is equal to 12. This is a false statement. X to the 3 times x to the 4 is equal to x to the power of 3 plus 4, which is x to the power of 7, not x to the power of 12. Here's the reasoning for that. X to the 3 times x to the 4. Something raised to the power of 3 means you're multiplying it by itself 3 times. Something raised to the power of 4 means you're multiplying it by itself 4 times. If we stack all these together, we get 7 total. And something multiplied by itself 7 times is that thing raised to the power of 7, not raised to the power of 12. The next statement is false. Here's why. X plus a cubed is equal to x plus a times x plus a times x plus a. And we have to FOIL it. So if I FOIL the first two together, I'll get x squared plus 2xa plus a squared times x plus a. Now if I FOIL that together, I have to do that in a few steps. Get x cubed plus 2x squared a plus a squared x plus ax squared plus 2x a squared plus a cubed, and then collect like terms, x cubed, and then we have x squared a and a 2x squared a, so plus 3x squared a, and then we have a squared x and 2a squared, so plus 3a squared x, and then plus a cubed. So it's not equal to x squared plus a cubed, it has cross terms. And those were missing inside that statement. So this is a long way to say, this false example is a long way to say that if you have two terms in a bracket added or subtracted from each other, raised to a power, you can't just apply the power to each component in that bracket separately, because there are cross terms there. Okay, the next statement. A over b plus c is equal to a over b plus a over c. Very tempting statement to do. This is false. And to show that it's false, I'm going to simplify the a over b plus a over c. A over b plus a over c is equal to, in order to add these two quantities together, we have to make common denominators. So multiply top and bottom of the first expression by c. Multiply top and bottom of the second expression by b. Now the bottoms match. We have ac plus ab over bc. Common factor in a out. A times c plus b over bc. And that's not equal to a over b plus c. It's not even close. Okay, next statement. Negative 2 to the power of 4 is equal to 8. This is false. Negative 2 to the power of 4 means negative 2 multiplied by itself 4 times. So negative 2 times negative 2 gives you positive 4, times negative 2 gives you negative 8, times negative 2 again gives you positive 16. That's not negative 8. Okay. 16 to the power of 3 over 2 is equal to 24. Well, that would be 16 multiplied by 3 over 2. But what does power 3 over 2 mean? The 2 in the denominator of an exponent refers to the root number that's there. So 2 means square root. Then the 3 gets applied after the root. So the top number is the exponentiation number. The bottom number is the root number. That's the shorthand for a fractional exponent. Square root of 16 is 4. 4 cubed is 4 times 4 times 4, which is 64. So this was false. Okay, next problem. True or false? 7 to the 0 is equal to 0. This is false, because 7 to the 0 is equal to 1. Anything to the 0 except 0. So any non-zero number to the power of 0 is equal to 1. Here's why. Since what's x squared over x squared? Well, we know it's equal to 1. And we know, equal to 1 because we can cancel top and bottom. And we know that x squared over x squared is equal to x to the power of 2 minus 2 from exponent laws, which is x to the power of 0. Thus, x to the power of 0 is equal to 1 for all x not equal to 0. We'll talk about the special case of 0 to the 0 in calculus. Okay, next problem. Is it true that x squared minus 16 is equal to x minus 4 squared? Well, I'm going to answer it backwards. I'm going to show that it's false, because x minus 4 squared is equal to x minus 4 times x minus 4. If we FOIL it out, we get x squared minus 8x plus 16. We get a cross term of negative 4x, another cross term of negative 4x, combined like terms, we get negative 8x. Negative 4 times negative 4 gives you your positive 16. That's not equal, not even close to being equal to x squared minus 16. Okay, next one's almost the same. Can we say that x squared plus 16 is the same thing as x plus 4 squared? This is false. Very similar to two problems that we've already looked at. X plus 4 squared is equal to x plus 4 times x plus 4, which is equal to x squared plus 8x plus 16, which is not equal to x squared plus 16. It's missing the cross term. It's missing the 8x. Okay, last problem on this page. X to the 4 all to the 5 is equal to x to the power of 9. Well, this is false. Here's why. I'm going to give you two answers. One of them is a formal statement of exponent laws. X to the m to the n is x to the m times n, not x to the m plus n. So x to the 4 to the 5 should be x to the power of 20. Not x to the 9. I will explain why. X to the 4 all to the 5 means x to the 4 times 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 x to the 4. And each of those x to the power of 4 is just 4x's multiplied together, and hopefully I can fit this all in one line. Yep. There, okay. Now we count up how many x's there are. There's 20 of them if you count them all up. So we get x to the power of 20, not 9. Okay, next page. Part J. Sine of x equals 0 means x is 0. This is false. Sine is a periodic function. Sine of x equaling 0 has several possibilities. Sine of 0 is equal to 0 is true. But sine of pi equals 0. Sine of 2 pi equals 0, etc. There are many x values, not just x equals 0. That's only one of the solutions. Okay, next problem, next question. Sine of 4x over 2x is equal to sine of 2. This is false. It's one of the things you're going to be tempted to do in several calculations in the course, is to do bad canceling. So we can say that sine of a over b is not equal to sine of a over b. In general, there are some exceptions, of course, like for example, if b is equal to 1, dividing by 1 doesn't change anything, whether it's inside the sine argument or outside the sine argument, but any other situation, it's going to be screwed up. I can show you a particular example. Sine of 4 times pi over 8 divided by 2 times pi over 8. So what I'm doing in this example is I'm let x equal pi over 8. I'm just choosing one particular example to show that you cannot do this. Okay, if we plug that in, we're going to get sine of pi over 2, or sorry, pi over 4. Oh, I'm going to pick pi over 4. I'm a big liar. I'm changing my mind. Come on, erase, erase. Okay, I'm going to let x equal pi over 4 instead of pi over 8. Wasn't thinking properly. Okay, so 4 times... Oh no, I'm not a liar. I was right to use 8. Yes. Okay, so sine of 4 pi over 8, that's going to be pi over 2. That's what I wanted. So yeah, pi over 8 was right. It was correct to do that. 2 pi over 8 is the same thing as pi over 4. The 2 and the 8 partially cancel. If you remember your high school trigonometry with radians, I don't know if everyone did radians or not, but what pi over 2 means is it means 90 degrees. Sine of 90 degrees is 1. So we have 1 over pi over 4, which is the same thing as 4 over pi. Double fraction. 1 divided by pi over 4 means 1 multiplied by the reciprocal. 1 multiplied by 4 over pi, which is just 4 over pi. While sine of 2 is equal to something from a calculator. And whatever that calculator number is, it can't possibly be pi over 4. Pi over 4 is larger than 1. So sine functions, the y value of a sine function can't be larger than 1 or less than negative 1. And sine of 2 can't possibly be 4 divided by pi. 4 is larger than pi, so 4 divided by pi is larger than 1. So that's an example showing that this statement can't be true. Just one counterexample is enough to disprove it. Okay, and then question L, true or false? A plus B over C is equal to A over C plus B over C. This is true. The first true statement. And we can think about this in terms of going backwards. A over C plus B over C, they already have a common denominator. So we just add the numerators together, A plus B over C. Since already common denominator. Just making the statement backwards. And I want to contrast that with the statement that was above. It looked very similar. Statement C, A over B plus A over C, that did not have a common denominator. And it's all like, it's completely messed up. Like you can't do anything that's anything like this for option C. So this is a roundabout way of teaching a little lesson about working with fractions. We're going to have lots of opportunities to use the property that's indicated under question L to take a fraction and break it up into 2 fractions or 3 fractions or 4 fractions. We'll have reasons to do that. Okay, question M. True or false that log of A times B is log of A times log of B? Well, this is definitely false because we have a log property that is different than this. The log rule from a grade 12 functions course or algebra 2, or it's called different things in different school systems. One of the log rules is that the log of 2 things multiplied together, I'll call them m and n, is equal to the log of the first plus the log of the second. So log of A times B is log of A plus log of B. They're not multiplied together. Okay, question N. Log of x to the power 3 is equal to 3 times log of x. This is true. It's a log rule. That the log of m to the power of n is equal to n times the log of m. So there's this big list of log properties. And we'll go through them in class. We'll go through them as part of the review. But one of them is this. And it's tempting to misuse this log property in problems that have a step that look like question O. In question O, it asks, is it true that log of x to the power of 3 is equal to log of x all to the power of 3? And this is false. And I can give an example. Let's look at log of base 10 of 10 to the 3. That's equal to, using the log rule up above, 3 times log of base 10 of 10, which is 3 times 1, which is 3. While, if we look at the other side, log of base 10 of 10 to the power of 3 is equal to 1 to the power of 3, which is equal to 1. And 3 is not equal to 1. So the brackets are really important. Is the power 3 being applied to the entire log function, or is the power 3 only being applied to what's inside the argument of the function? If it's being just applied to what's inside the argument of the function, then you can use that log property to bring the power down. But if it's applying to everything around the function, log itself included, then you can't use that property. That property only applies for power that's applied to the argument of the log itself, not to the entirety of the log expression. Okay, Q. Is it true that x divided by root x is equal to the root of x? And this one's true. Oh, I skipped P. Oops. Almost skipped P. Caught myself. Square root of x squared plus 16 is equal to x plus 4. This is false. We could try, for example, So look what happens at x is equal to 3. Now if you check it at 0, you're going to find it works, but that's the only value it'll work for. So I'm going to check x equals 3. So square root of 9 plus 16 is equal to 3 plus 4. So this says the square root of 25 is equal to 7. This says 5 is equal to 7 is false. So one counterexample is enough to say something is false. It doesn't work for x is equal to 5, x is equal to 3, and anything else we check except x is equal to 0 will reveal the same thing. I just picked 3 because it square roots perfectly. Okay, question Q. Is it true that the square root of x, or x divided by the square root of x is equal to the square root of x? So there's a few ways we can do this. One of them is to note that x is equal to x to the power of 1. 1 can be split up as 1/2 plus 1/2. And we can write this using exponent laws as x to the 1/2 times x to the 1/2, which is root x times root x. It's a long, you could just start with where I ended. You could say x is equal to root x times root x if you want. So thus, x over root x is equal to root x times root x over root x, and we can cancel root x's, and we get the square root of x. Okay, next question. True or false? Sine squared x. Oh, so I forgot to put this was true. Okay, so next question, is it true or false that sine squared x plus cos squared x is equal to tan squared x? This is false, since the trig identity, one that we will use in this course, is sine squared x plus cos squared x equals 1, is the actual trig identity. This is a fake trig identity that was there. Okay, and then the last one, true or false? 7 over 6 minus 5 over 3 is equal to 2 over 3. Can I just subtract top minus top, bottom minus bottom? This is false. You can't do that unless you make common denominators. You can't do subtraction. 7 over 6 minus 5 over 3 is equal to 7 times, well, I don't even have to do anything to the first one. 7 over 6 minus 5 times 2 over 3 times 2 to make the denominators match. So 7 over 6 minus 10 over 6, which is negative 3 over 6, which is negative 1 over 2, and that's not equal to 2/3, not even the right sign. So there's quite a mix of levels of mathematics in here, from whenever fractions was done, if that was in grade 8 or grade 9, whenever trig was done in grade 11 and 12, and then the exponentials and logs. Some of this is hit and miss. This may not be review for you. Some of the log material, depending on who your teacher was. Grade 12, you may not have done all the log properties. Square roots and all the squaring stuff, that shouldn't be news. Just need a little bit of a reminder about how that stuff works. This is all super important stuff. You get tripped up on this all the time if you're not looking for it.